Hello, everyone. Welcome back. Today, we're going to talk about an application of compound interest, which is about the future value of an annuity, and sinking funds, which are related to each other. Explain what those are and then how to calculate them. So our goals are to understand first what annuity is, what that means, and then also be able to calculate the future value of an annuity, then understand what a sinking fund is, and also be able to calculate the periodic payment for that. First, let's talk about an annuity, then be able to calculate its future value. So an annuity is any sequence of equal periodic payments. So in that sense, like paying off a car or a house loan is a annuity in that sense. And so what you're often doing is you're making payments, but then there's also some interest involved as well. Okay, you're generating these payments. Basically, they're going into a bank somewhere. They're also generating interest on their own. So the total amount, your total amount is not just the amount of all those payments after however many years, but then is also the interest also is accumulated depending on what interest rate you have and also what compounding period. So an ordinary annuity is a payment that's made at the end of each time interval. And that can also be important depending on how the interest is calculated, whether it's the end, or beginning, or middle. Future value of an ordinary annuity is the sum of all the payments plus the interest earned, what we mentioned before, as given by this formula, where FV is your future value. That's the amount at the end of the payment, of all the payments. Of course, PMT is your payment. That's your periodic payment. Here we're calling it periodic because it could be monthly. But it could also be, 4 times a month, twice a month. Could also be 4 times a year, twice a year, maybe even just once a year. Just depends on what the terms are. Then I is your interest rate per period. This is the same as used in the compound interest formula. Basically, it's your annual interest rate as a decimal, then divided by the number of compounding periods per year. And then N is the total number of payments. So the years then times the number of payments per year. That's the formula. So let's do an example over on the right. Let's see how this works. So it says USG Annuity in Life offered an annuity that pays 7.25% compounded monthly. If $1,000 is deposited in this this annuity every month, how much is accumulated after 15 years? Let's take a look. See what we know. Okay, so from our formula, what we need, of course, is our payment, and that's $1,000. And this is going to be deposited monthly, so every month. And also, that period is going to be the same as our compounding period. Okay, now our I is our interest rate. It's basically R. Think about compound interest is R over M, whereas our interest rate is a decimal, so 0.0725 divided by the number of compounding periods, which is 12. And if you divide that, what you get is and I'm actually going to use all these decimals. So 0.00604167. I'm going to keep all those, make it as accurate as possible. And also then my N is my number of compounding periods, the total number. So that's going to be my time T times M. Okay, the time in years times number of compounding periods per year. This will be 15 times 12, which is 180. So then the future value is going to be 1,000. Just plug everything in times 1 plus I, which is 0.00604167, raised to the N, which is 180. This is minus 1, and then this whole thing. You can also include the 1,000 in the decimal as well. It doesn't matter, but all this include the minus 1 is to the I, which is once again 0.00604167. Okay. Now to calculate this, we're actually going to use use a graphing calculator, whatever means you want. I'm going to use Desmos to do this for us, because we'll be able to see it well. So we have 1,000 for the space. Then I'm going to go and combine those. So 1 plus I is going to be 1.00604,167. Okay. Now that's going to be raised to 180. Okay. Then that's minus 1. Now let's close the parentheses, then divide that once again by that decimal. Not the 1, just the decimal, the I itself, 0.00604,167. And that gives us our value. So our value, as you can see, is $323,943 and around the nearest cent, 19 cents. So that's the value then of that annuity after, once again, so you're making monthly payments, $1,000 each month, okay? And then that's the amount after that. Now, also, if you, we'll do this just a moment. So let's go back here. Let's write that down. So our answer then, the future value, and actually I need a little space. So let me grab the future value then is, as we just said, this annuity, $323,943.19. Now, another question might be is how much this is interest. Okay, so let's find out the total amount of the payments. Let's make a little more space. So the total amount of the payments write that better. Total amount of the payments. Okay, you know it's going to be $1,000 or $1,000 times. We have a total of 180 payments to make times 180, and of course that's just going to be $180,000. So you can see the total amount is much more than that. So then the interest is equal to the future value minus, I'll just say payment total, which is going to be 323,943.19 minus 180,000. This also gives you an idea of the accumulation of interest. And so that's going to be, what's that going to be? So that's going to be 143,943.19. So it's almost, well, the interest amount of interest is generated almost as much as what you paid into it. That would be a good annuity. If you get that rate, that would work well. If you're thinking about setting up a long-term fund for 15 years, like a college fund or something like that, that's pretty good. Now, so that's how this formula then works. So to find the future value, you have to know the amount of your payment, now whatever your payment period is. Then to calculate your interest rate per that period. So your interest rate is usually be given as an annual rate, then divided by the number of compounding periods to get your interest rate per period versus a decimal. And then the n is your time in years times the number of compounding periods and the total number of payments you're going to make. And the number of compounding periods is the same as the number of payments. The timing is the same for the number of payments you make as well. Okay, next, let's take a look at this. So let's talk about something called a sinking fund, which is related. So a sinking fund, so if an account is created for accumulating funds to meet future obligations or debts, is called a sinking fund. Okay, So that's just simply a choice if you're creating this account once again to meet some future payment you want to make in the future or debts. It's called a sinking fund. So it's basically the same sort of thing, except that's how it's defined or classified. Now, in this case, so the question is, and often the difference here is in the annuity, the regular annuity like this, the future value, you plan to make a certain number of payments and you determine what the future value is going to be. If you have in mind what you want your future value to be, then you need to know, depending on what interest rate you have in a compounding period, what your payment per period is going to be. And so here we can actually determine this just by solving this formula for the payment. So that we can find the payments necessary to meet whatever that amount is. Let's take a look at this over here on the right. And this is an example. The parents have set up a sinking fund in order to have a $120,000 in 15 years for their children's college education. How much should be paid semi-annually into the account, paying 6.8% compounded semi-annually? Okay, a couple of things to remember. So semi-annually equals 2 times per month, per year rather. Okay, so since you're compounding, also you're paying into it twice per year. So I need to find the same thing, essentially the same formula, just solve for the payment instead of for the future value. So our I, once again, is going to be the interest rate is a decimal, which is 6.8 or 0.068 divided by the number of compounding periods per year. And that's just going to be so our interest per compounding period is going to be 0.034 or 3.4%. Then our N is going to be our number of total payments, the same as a number of total compounding periods. So it's going to be 15 years. So 15 times 2 twice a year is going to be 30. Okay. So if we plug all this in, then the payment, also then our future value, write that up here. So our future value, of course, is $120,000. So that's the goal we're trying to get. So the question is, what payment do I need semi-annually or twice a year to make that happen? So we plug this in. So our future value is $120,000 times. Actually, I don't really need that at the moment. So then times 1 plus 0.034. This then is going to be raised to the 30 minus 1 over 0.034, the I. And once again, you can also put the future value of this amount over that as well. Now, let's go back to Desmos and do this. So let's start another line in the same way. So $120,000, I'll make a space. And then I'm going to raise 1 point, I've added those 0.034 raised to the 30, the number of payments or number of compounding periods, minus 1. And then divide that by that interest rate I of 0.034. And okay, hang on, something is not right. Oh, okay. Sorry, I realized what I did it backwards. Hang on. I apologize. Let me go back. I did upside down. So let me erase that. I apologize. Yeah, the formula looks like this. So let me change that. So this time we have our interest rate I on top, so 0.034. Yeah, I just did it upside down. That's why it was off. But that's a good thing to understand. Make sure your number makes sense. So 1 plus 0.034 to the N, which is 30, minus I. Okay, let's try that again. Go back to Desmos. 0.034 divided by, then we have 1.034 raised to the 30th, and minus 1. Now, that gives us our amount then. So about $2,363, and the nearest cent 7 cents. So this then is going to be, as it says, $2,363.07 twice a year. Semi-annually means twice a year. So they're paying that twice a year, and at those rates, paying that twice a year at those rates, you'd have at the end of 15 years, you'd have $120,000. Now, once again, you can also determine from that, you can also figure out, like we did in the first example, the amount of interest generated from that, then also compare. Okay, one final question. Let me move this up a bit. Now, this one asks, a person invested $2,000 annually in an IRA. This is an individual retirement account, so basically an annuity, an ordinary annuity. At the end of 6 years, the amount of the fund is $14,000. What is the nominal compounding rate that has been fund earned? Okay, so this nominal compounding rate, what it is we're trying to find, essentially find the annual interest rate. Okay, we'll approximate that. So the same kind of annual interest rate we've used before. Now, so what it is we're doing is this is also just as, once again, this is an ordinary annuity. Let me say is an ordinary annuity, because in this case we're not talking about a sinking fund. Didn't ask us about that. So one point I find the interest rate, and this is an ordinary annuity. Let's figure out what we have then. So invest $2,000 annually. That's going to be our payment. So our PMT is going to be $2,000 annually. Okay. And then, so basically that's also our compounding period. Okay. And our future value, it says we want it to be $14,000. Now, what else do we know? Well, we also know that our N is going to be our number of years, 6 times our number of compounding periods. And since it's annually, that's going to be 1. So our M is going to be 1. So N is just going to be 6. So we need to find our I. That's our unknown. And this is also going to be, this is annually, then I is just going to be whatever the number, whatever turns out to be, is just going to be our annual interest rate. Now, so we plug all this in to this formula to see what we have. So we have then is the future value, which is $14,000, is equal to the payment, which is $2,000 annually, times 1 plus I. And once again, I is our unknown in this case. To the N, which is 6 minus 1 over I. Now, here's the thing. We can't actually solve this in a normal way. All right, because we have an I here, which is inside this, which is raised to power. They also have an I out here. There's no way to get I by itself. That's what we mean we can't solve for I. So what we need to do then is approximate with a computer. Okay. Now we can do it differently. We could plug it. We could use a computer program. We can also use Desmos. We'll show that again. We'll actually use that. We can actually use Desmos. What we're going to do is we're going to graph. We're going to make this essentially a function. We're going to graph y equals basically this. So 2,000 times 1 plus I to the 6 minus 1 over I minus 14,000. Okay. Now, essentially, if you solve this, subtracted 14,000 both sides, you get this. And so what we're going to do then is we're going to find out where this is 0. Okay. So if you subtracted that, you have this equal to 0. So I'm going to find out where this is 0. Okay. So I want to find x where y equals 0. Essentially, that's the x-intercept. If you've done graphing for a while. Let's take a look at this then on Desmos. So what we're going to do is just do that. So 2000, then in parentheses, 1 plus, and we'll call it x instead of I, the same idea, raised to the 6 minus 1. Now I need to put parentheses around this as well. Then divided by x. Now we'll graph that, but that's not it though, entirely. So then we're going to do minus 14,000. Okay. Now we want to find out where this is going to be 0. Okay. Because that's going to tell us where these two things are equal. And so we need to zoom in a bit. You can see there's a spot right here. And unfortunately, Desmos, if I click on this, it actually gives me that value. And that's going to be approximately 0.0614. I is approximately 0.0614. And so what that means then, so that then is going to be 6.14% annual interest rate. So that's the annual interest rate. So for our conditions we have, so once again, let's see what we started with. So if we're going to make $2,000 annually into an IRA for 6 years and compounding annually, and want to achieve after that 6 years of $14,000, then the interest rate we need to make that happen is this, about 6.14%. And this is also pretty easy to do in your head in terms of how much you paid in. So 2,000, if you pay 2,000 a year for 6 years, that's $12,000. So if it's 14,000, then in that 6 years, you've generated $2,000 of interest. It's not too bad. Now, once again, it may be difficult in real life to get that kind of rate, but that's what that shows. So in this case, in some cases, real life examples, you can't always solve things exactly the way we want to in an algebraic way and by hand. So we have to use a computer or calculator to help us out. That's what we did here. Because once again, so where these things are equal. So what I did is if I just subtracted this from both sides, I get this, and then where this is 0, then is where these are equal. That's what we look for in the graph. And the x that gave us that was about 0.0614. That tells us that the I that makes that happen, is about 6.14%. So what we've learned so far today is that we understand what an ordinary annuity is and how to find the future value given the payments, interest rate, and the number of years. We've also learned what a sinking fund is and how to calculate the payment you need to get some specific future value for those same type of requirements. And then we've learned also, if you have a future value in mind in the payments, what interest rate you'll need to accomplish that. Thank you. Have a good day.